Well, hello there. Recently, I challenged Rachie 50 to explain the variation in gravity that's seen that correlates with latitude. Now, her objection was that maybe it hasn't been measured accurately enough to show that this phenomenon actually exists. Well, in searching through on the subject, I found this video by Geoscience Australia called the 2019 Australian National Gravity Grids Data Release. Link is in the description. Now, it's about an hour long, and a lot of it is not particularly relevant to the subject at hand, but there are some basics explained from about 4 minutes 45 to 7 minutes 30, and there's a longer section from about 28 minutes to 39 minutes, which details how they tease out the variation in gravity that's due to the underlying geology. Now, amongst many reasons, it's particularly useful for the mining industry so they can identify locations that are probably worthwhile digging up. Now, along with the release of data, there also was the introduction of a web portal to access the data. And here we can get the entire National Gravity Database on a map here, and it consists of about 1.4 million individual observations of gravity. We zoom in here on a particularly remote section of South Australia. We can see that there are gravity observations taken, roughly speaking, with a spacing of about 10 kilometres apart. Now, this is pretty typical for the country. In fact, most of the country has a spacing of about 6 kilometres or less, and there's only some smaller sections of the country that have up to about 10 or 12 kilometres of spacing. If we look at an area in central New South Wales, we can see a pretty typical part of the grid where the east-west spacing in this case is about 2 kilometres and the north-south spacing is about 5 kilometres. By contrast, if we go to the Tom Price region of Western Australia, where there's a little bit of mining activity going on, the higher density grid on the left side of the map here has a spacing of, I think, about a kilometre or less between those dots. And those lines are very intense observations, which sometimes have a spacing of less than 50 metres. Now, 1.4 million data points is probably a bit too much for our purposes here. So what I have concentrated on here is the fundamental gravity network. This is a network of around about, I think, about 900 observations. Now, all of these observations were done by absolute gravimeters, so they are to the highest standards possible on the during the time that they were taken. Now, if we look at one of them in particular, I'm going to pick this one down here at Busselton, south of Perth in Western Australia. We can see that it was visited and measured in 1967, and it was observed to have a strength of gravity of 9,795,750.82 micrometers per second squared. Now, that number sounds a little bit unwieldy, but if we think about that in terms of meters per second squared, it is 9.795 meters per second squared, a much more recognisable strength of gravity. Now, I'll also express it in terms of another unit called the microgal, which actually gets rid of the decimal points, makes it a little bit easier to compare numbers. And we see that at that location, it was 979 million microgals. So in rough terms, the strength of gravity on the surface of the Earth is just shy of 1 billion microgal. Keep that in mind, 1 billion microgal, when we move on to some of the next section. Now, where did the data come from? Well, starting in 1950 and proceeding to the mid-1960s, there was about 250 observations of gravity done across Australia using a pendulum absolute gravimeter. Now, they work on the principle that the period of oscillation of the pendulum depends only on the length of the pendulum and the strength of gravity. So if you're able to measure the oscillation period quite accurately and measure the length of the pendulum quite accurately, you can derive the strength of gravity at that location quite accurately. Now, from the early 19th century to the mid-20th centuries, these were the absolute standard in absolute gravimetry. Now, this only changed in Australia in about 1979 when this particular Soviet gravimeter was brought over to do some observations. This is a free-fall gravimeter, and it consists of a mass that is dropped through an evacuated tube. There is a laser interferometer in there to measure the location of the mass as it falls through the tube, and consequently the rate of acceleration that can be derived from those measurements. Now, here in Flat Earth Research, you are all very interested in vacuums, and the tube in this apparatus was evacuated down to a pressure of about 1 millipascal, and in other units, that's about 1/100 millionth of an atmosphere, around about a 10 millionth of 1 psi, and in our favourite unit of all, it's around about 10 to the minus 5 torr. So remembering that the strength of gravity is approximately 1 billion microgal, this particular gravimeter was reckoned to be accurate to 15 microgal. So it's an extremely precise instrument. Now, it was only taken to 5 locations in Australia and 1 location in New Guinea. Now, that may not seem like much, but consider that the entire package of equipment was about 800 kilograms, so it's not very portable. And at each of those 5 sites, it did 2,500 drops of the weight. So quite a lot of time, quite a lot of data, and the purpose of it wasn't to remap the entire country. The purpose was rather to provide a more accurate datum to which the older data could be tied and to which new data could be tied. Of course, this type of equipment has stayed in use since then, but is much smaller, much more portable, much more affordable, much quicker to use, and much more accurate. In the early 2000s, Geoscience Australia started using some that were accurate to just 2 microgals. So extremely, extremely precise instruments. So now to the actual data. So Geoscience Australia released the entire 1.4 million observations. Now I've taken about 400 of those, which were done by absolute gravimeters and that are part of the fundamental network. Now, interestingly enough, there are still some observations that are included from the 1950 surveys. They are still considered good enough to be included today. Now, amongst all the different parameters, quite a few of them that each data point has, the ones I'm particularly interested in is the latitude of the observation site and the strength of observed gravity at the observation site. Now, I've also taken the geoid height, which in rough terms is the height above sea level, though not exactly. And I'll come to the reason why I've taken that in a moment. But the first thing is that we take the latitude and the observed gravity and we plot them against each other, and we get this. We can see that we have a quite clear trend that as we go from minus 35, which is 35 south latitude, to around about minus 12 latitude towards the equator at the top of Australia, we find that gravity decreases in quite an obvious pattern. Now, there is a bit of spread amongst all these numbers, and that's where I've then gone and done some height corrections. Now, the reason being is that because of the oblate nature of the spheroid that the Earth is, we find that the closer you are towards the equator, the further you are away from the centre of mass of the Earth. This picture is quite exaggerated. And also, the further you are above sea level, so you're up on top of a mountain, the further you are away from the centre of mass of Earth as well. So I've done some very crude calculations to control for that. But by doing that, this set of data becomes a much tighter match. So still, what we can clearly see is that as you head up towards the equator, gravity gets less. And that is exactly as predicted by a rotating sphere. Now, of course, the globe has a perfect explanation for this. We can think of gravity as mass attracting mass, and that's the reason why objects are drawn towards the centre of mass of the Earth. And the variation that we see with latitude can be explained by the Earth being a rotating spheroid and the different amounts of centrifugal force that is produced because of that. Now, to Rachie's objections, are the measurements perhaps not precise enough? Well, we see here on the variation of observed gravity with latitude, this variation happens in about the third or fourth figure of precision. Now, if we remember from early on, the equipment that's being used to make these observations is actually precise down to about 8 or 9 figures, so definitely precise enough to see the 4 figures sort of variation. Now, are the observations not accurate enough? Well, the overall aim of this is to understand something about the underlying geology. So in order to do that, we do things like take into account known factors, things like latitude, the oblateness of the Earth, There are other factors, which I won't go into, but once all those factors are taken into account, what you're left with is hopefully enough to identify the underlying geology for one particular purpose. And as can be seen by the amount of time and effort and money that mining companies spend roaming around their lands using gravimeters measuring gravity, if it wasn't worth it, they wouldn't be doing it. So it is definitely accurate enough to measure the very small variations due to local geology. Definitely accurate enough to measure the variation due to latitude. So, what is the flat Earth explanation for this? Well, we often hear that gravity is actually explained by density and buoyancy. Well, if that were the case, then it shouldn't vary anywhere on Earth. So this gravimeters used anywhere on Earth should produce the same numbers. After all, it's the same tube evacuated to the same level of vacuum. It's the same mass being dropped in it. It's the same interferometer measuring the falling of the mass. It's the same equipment doing the measurements and the calculations based on that. So it should produce the same results all over the Earth within a small range of variation. But as we can see, it doesn't. It produces different numbers. So what's the explanation? So thanks for watching. It's all over for the globe. There's no coming back from this one.